Here we are in chapter 16, and we're in really the home stretch of the course, and we get into what I think is some of the more important statistical machinations, so to speak, and that's linear regression. You'll see regression a lot in the literature. It's hard to find an article without it, to be quite honest. You'll see ANOVA, different types of ANOVA, and you will see regression and different types of regression. We're going to work with linear regression and multiple regression. We'll start out simply with linear regression, and then we'll take a look at multiple regression, which is a bit more challenging. And you've seen simple linear regression before. I'll show you that when we get into the mechanisms. Multiple regression, probably not so much. And again, we're just scratching the surface of regression. You'll have enough information probably to be dangerous. But you'll be able to, at least by the end of this, run a multiple regression analysis. Now, when you actually run them, there's an awful lot more involved. Like there's about 6 different steps you have to go through to make sure you're not making any errors on the way. I'm not going to cover that. That would take us another week or two to move through that. But you will be able to run a basic one and also do an interpretation of an SPS output. And further to that, you should be able to recognize one and interpret what you see in the literature. That's a big part of this course is, I know a lot of you may never have to use statistics. You're taking this course because you have to. But I'm hoping that some of the material will come to mind when you read journal articles, and you'll be able to go, okay, this makes a little bit more sense now in terms of what I am reading. So that's what we're going to do for this part of the course. Without going into a lot of detail with respect to the learning goals, really we're going to get into how linear regression works. What does it do, right? What does it do? I can tell you right at the beginning, it does one of two things, and sometimes in combination. It explains findings that we see in the literature. It also helps to predict future findings or future outcomes. So it does two. A lot of times we like to look at it for predicting. I was kind of schooled on that a little bit by one of my PhD committee members who is a measurement specialist, and he said, Mike, it's always safer just to say what we're explaining here in the present tense, because unless you're going to run a prediction, you really shouldn't say that unless you do it. So it does two things. We develop these what we call these explanatory or predictive models of future behavior or future outcomes in variables that we are interested in. And I'll give some examples of that coming up. And we'll talk a little bit about how to assess the accuracy of predictions as well. Before we get into more about the explanatory power of linear regression, I want to draw us back to what we just finished, and that was correlation, because you're going to see correlation appear again. As a matter of fact, you're going to see R squared show up. This is why I spent some time on the coefficient of determination with you in chapter 5. You're going to see R squared make an appearance. And so remember what correlation does. Correlation helps us explain the value of one variable based upon the value of another. If I see a change in one variable, I can actually use that to kind of assess what change is going to happen in another variable if those two variables are related. If they're not related, then nothing doesn't really matter. There's nothing really to work with here. And we call those variables x and y, as we did in chapter 5, and you're going to see x and y again in linear regression, right? So just to kind of give you a background, correlation to a certain extent makes an appearance with linear regression. And again, just a reminder that we look for the strengths of the relationship, right? We talked about the highest absolute value of the correlation coefficient, right? That's important. And why was this important? Well, it's important in the sense that the more two variables in common, we talked about that shared variance, that kind of tricky one, the more you know about one variable from the other. And there's that R squared again. And so you're going to see how regression models, in terms of when we put them together, we talk about explanatory variance or shared variance. How much of this either 1x or, in the case of multiple regression, more than 1x's, how much together, right, do they explain the change that we see in the y variance? Now, I touched on some of the terminology in this slide before when we were working with two-way analysis of variance. And so when we talk about explanatory variables, for example, and outcome variables, we saw that in two-way ANOVA, and we see it here again in regression. And so these explanatory variables are called the independent variables. These are the ones that the researcher can actually manipulate, right? So an example of an independent variable might be, again, like I used very simply, a level of a drug or level of exercise intensity, right? The researcher can manipulate those things, and we think, or the researcher thinks, that those independent variables are going to cause a change in the dependent variable, right? And so in that sense, and that's the variable that the researcher is interested in. And so the dependent variable, and this is how I finally memorize these, because I always got these mixed up in grad school. The dependent variable depends on the independent variable, right? Whatever change in the dependent variable occurs, that actually depends on the influence of the independent variable. Those are the things that the researcher has some control over. Now, if there's some statistical significance there, we'll see a change. If there's not, we won't. In those cases there, we say that, well, the independent variable has no effect on the dependent variable. And again, we call the dependent variable the y variable, and the independent variable, that's going to be our x variable. So we're building up here to actually get into the model itself, and I'm sorry for taking so much time. I just want to make sure that we're grounded. And as a matter of fact, you're probably looking at this. You're probably going, Mike, isn't what you're talking about the same thing as correlation? And hang on to that thought, because that actually comes back a little bit, at least with simple linear regression. So just again, this is what regression modeling does, right? Regression modeling explains changes in dependent or outcome variables based upon the changes that we see in the independent variables. Again, that the independent variable is the one that the researcher can manipulate. It kind of drives what we think is going to be happening in the outcome, or the dependent, or the y variable. Regression modeling also takes a look at the strength of the relationship between the two, and that's the R-squared aspect of it. And then also it takes a look at what we call the statistical significance, because just like anything else in statistics, I can put together a model that I think explains something really, really well, and it might not be statistically significant. In other words, what I saw actually happening really happened by chance. And so we never get away from that aspect of statistical significance. Let's get into some examples here then and kind of move us along. So the first example I have up top is a very simple linear regression type of equation, right? I'm interested in the retail price of gasoline in the Vancouver area, and I think that the price of crude oil has an effect on the price of gasoline. You know, my research hypothesis might be, well, if the price of crude oil goes up, I can expect an increase in the price of gasoline in Vancouver. That's a reasonable research hypothesis, right? Now, what I don't know is by how much or by how little, you know, that change in Vancouver gas prices is going to be. And that's kind of the second part of regression. And this is what makes it different from correlation. The price of crude oil can explain, in part, the price of gasoline in Vancouver. But what correlation can't do, and what linear regression can do, is predict, or is create a model for predictive prices in the future, right? So if I want to know what the price of gasoline in Vancouver is going to be when the price of oil goes up by a certain factor, I can put together a model that will get me, hopefully, pretty close to that estimate. And this is that extension. Explanation, correlation does that, simple correlation. But prediction is where regression has a leg up on correlation. But take a look at the second example here. Now we're looking at something that you might be interested in the social sciences, for example. I might be interested in annual income. What factors influence annual income? And so you go and do a bunch of reading, and you find out there's all kinds of factors that can affect one's annual salary. The hours of work that one does, one's level of education, the type of occupation. Are there gender issues in the workplace? Age aspects, the region, years of experience, unionization status, etc. You might have 5 more, for example. All of those independently likely have an influence on one's annual salary. So, but we also know that all those things kind of go together. Are some of those related? And so, could you put together a collective? Here's a series of x variables that together, collectively, explain fairly well one's annual salary. And could we then develop a predictive model for that? And so the second example there is multiple regression, and it's much more challenging to work out a multiple regression model. Just a quick slide here, a bit of a sidestep from the previous one. And so we use regression. We take a look at the amount of change in the dependent variable y that results from the changes in the independent variables of x. This is what we do. And we saw that with the previous example. And here's 4 things below, just as examples in terms of what linear regression can do for us, right? It can even get into things like challenging current theoretical models that might be in place in our current levels of practice. Okay, I mean, as we gather more information, we adjust or we adapt the models. We saw this if you paid attention, the entire COVID thing these last number of months was all about changing predictive models. Okay, the more information that we have, okay, we have a new variable we want to put into our model. Is our new variable, does it add or does it take away from the model? Does it add or take away from the predictability of the models? It's more than simply just explaining things. We can also challenge current models that are used in practice as well. So this helps to modify things and improves our practice. I'm a visual learner, and so words help me out a little bit, but sometimes diagrams are better. And so this here on this slide is a bivariate or simple regression model. Bivariate means 2 variables. Bi meaning 2, and variate, of course, meaning 2 variables. So I've got 2 variables here, and this would be my simple regression model. Again, it looks like correlation, but it's not, as we're going to get into that. Here is my model for what we call a multivariate model, or this would be what you would see in a multiple regression. And what we have here, I kind of narrowed things down a little bit, and I've chosen my y variable here, which is my income variable, and I picked 4 of the independent variables from the previous slides. Right, so instead of having all 8, I've got education, sex, experience, and age. All of those might have an influence on my outcome variable here. Now, the one thing I want to draw your attention to, with linear regression and multiple regression, the y variable or the dependent variable here has to be a continuous variable. Okay, there's different types of regression where you can have an ordinal outcome or a dichotomous or like a bivariate outcome. It's going to be one or the other. Those are more complicated. That's ordinal regression and logistic regression. That's advanced regression. But for us and in our class, the y variable has to be continuous. It can be either interval or ratio. Now notice here that the x variables here, the independent variables, can be of any type of variable. They can be either nominal, they can be ordinal, or they can be continuous. So education here would be an example of an ordinal variable because you can rank education. Sex would be a nominal variable because it's categorical. Experience is a continuous variable, years of experience, and so is age. And so that's the wonderful part about multiple regression, is that although we're limited, right, at least in our case, with a continuous variable for y, we can use and import all different types of variables to explain it. We're not limited to continuous variables. Remember with t-tests we were limited, right? We were limited to continuous variables with t-tests and with analysis of variance, weren't we? But with regression, we're not. Now, it gets really tricky when you're trying to explain, right? If I've got different levels of education, for example, it gets a bit more challenging to explain what those different levels mean in terms of their output, their impact on y. But we'll get to that. One of Dr. Bruno Zumbo, he's the professor I took my regression class with at UBC, an outstanding statistician, one of the world's best, and also a phenomenal educator. And it was a great course. Learned a ton. And he kept coming back to this. So I paid attention to what he was saying. He kept coming back every single class. He goes, remember what we're talking about if we're trying to understand what regression does. And it's our model here. So in words, the data that we have, okay, so this is the data that we collect, is equal to the model that we developed from regression. And SPSS puts this model together for us. You don't have to sit down and work this out. SPSS does the machinations for us. But the data that we have collected, in other words, the real world, is equal to our model of explanation plus the error. Okay, so remember that there's always going to be, we're never going to get everything perfect. And so there's always going to be error with the models. We're never going to hit that bullseye exactly dead center, never bullet on bullet. So data could be considered the true state of things or the true state of the world. The model is the researcher's explanation of the observation or phenomenon that they see. And then you've got the error aspect here. Again, the model doesn't fully explain the state of the world, so error has to be accounted for. Sometimes we put these things in as correction factors. Sometimes we just recognize, okay, there's error with this model, it's the best we can do. Maybe another model will come along with less error and we'll use that model. And you can develop these models. I did one for my PhD. It's called hierarchical regression modeling, where we begin to build a model together, and the one that had the least amount of error and the greatest explanatory power, that was the final model. And so these things are not just necessarily one thing. You can actually build them. And so we have this here as an explanation of our model, or the script for the model, and its y is equal to beta 1x. I'm going to expand on this in the next slides coming up. So just to kind of give a sense of visualization, as you're going to see coming up, when we put together a simple linear regression model, we're talking about drawing a straight line between data points. And you kind of saw this with correlation. You kind of saw this with correlation, where you had a series of scatter plots or points, and they began to have some sort of shape, right? Some were more in a positive direction, some were more oriented in a negative direction, some were really close together, almost forming like a line of dots. Others were a bit more scattered, okay? And so what regression does, it takes into account all that data and draws a regression line through them. And I want to explain what that regression line is in the next few slides. And here we go. This again kind of gives us a sense of the visualization of what we're doing. And so again, the y is the dependent, or what we call the response or the outcome variable, and x is the independent or the explanatory variable. So what we want to do is we actually want to, and again, without any of the data on here, no data points, we actually want to draw a line between all the data points. That is what we call the best fitting line. And we'll talk about that later on when we talk about the ordinary least squares method of regression. And so what we have here, if I can actually draw a line between data points, what that also means is I can actually draw a slope of a line. Remember what slope was? Slope was the rise divided by the run. And that slope in simple regression is going to be your beta 1. So your beta 1 is going to be the slope of this here. Again, you don't have to worry about it in terms of developing it, because SPSS will do that for you. So our model is now y equals beta 1x. Now we know what the beta 1 stands for. That's the slope of the line, plus the a. Now the a is the intercept. At some point in time, you're going to have to cross the y-intercept, because with some data doesn't go down to 0. You actually start with something that is in the positive realm. And so this is kind of our starting point here. If this was age, for example, you wouldn't have an age being 0. That's kind of weird. But you might have age being here. It might be 20 years old, depending upon the type of population. So A simply stands for the intercept. So in building our model now, and again, this is our simple linear regression. It's different than multiple regression. I want to emphasize that. Right, so the regression model, then we've got two parameters to estimate, right? We've got the slope of the line, right? The slope of the line beta and the y-intercept are the two variables that we build to estimate what y is. Now understand the only thing that you have when you're building a model, going into building a model, and this is the data that you give to SPSS, you're going to have a number of X values and you're going to have outcome values in Y. You're not going to have this beta here and you're not going to have the Y-intercept. That's what SPSS will give you, okay? So again, this is what the model is going to be given the data that I have for X, our independent variable, and given the outcome that we see in our data, which is going to be the Y variable. An example at this point would be helpful, probably overdue. And the title slide is called the logic of prediction, but it could also be the logic of explanation as well, because before you can have prediction, you need to have explanation. But let's just say that could we build a model to predict first-year college GPA from high school GPA? Right, and so in this slide here, what would be our independent data? Well, the only thing we have at the beginning is going to be our high school GPA. We don't know what's going to be happening in the future yet, so we collect a bunch of high school GPA, right? And then we wait for our participants to finish their first year of college, and then we have their college GPA. So this would be our Y variable, right? So this is our X variable and this is our Y variable here. And then what we do is we begin to put together a model of explanation. And a great way to start our model of explanation is to go and graph something. Now you can't graph everything. You can't graph multiple regression, okay? It's just not possible. I'll explain why that is. But you can graph linear regression. And if you notice, it looks really similar to correlation, doesn't it, right? This is what I was getting to earlier on. We graph things, right? So the y-axis here is our college GPA and the high school GPA is our x-axis here. And we begin to see a pattern that begins to emerge here. It appears, right, looking at the data, that that an increase in high school GPA seems to have some sort of explanatory, possibly predictive power of what one's college GPA is going to be, right? But it's not perfect. It's kind of messy. This is still somewhat scatter plot-ish or shotgun-ish, but it seems to have some sort of direction. We're kind of missing some data points in here, which would be helpful, but we don't have that. So we've got all these data points here. Now you might just say, well, what's the correlation value? Mike, we've seen this before. It's like, you know, paying double to see the same movie. True, but we're going to extend our knowledge a little bit with linear regression. And this is the extension of simple linear regression on correlation. Okay, so what SPSS will do for us is it will put a line in between all the data points that best fits the data. And I'll come to this a bit later on, so I'm going through this with you slowly here. And so we call this the regression line. And you might wonder, well, why not have a line in a different place? So how do I know that's the best fitting line? I'll get into that. But what I want you to notice more specifically is if you notice that some data points are actually really close to the line, right? See this data point here and this data point here, 1, 2, 3, 4. You've got 5 data points that fall really, really close to the line. But then you've got a bunch of other data points that fall actually far away from the line. Okay, and so if you notice, each one of these data points, it's not, except for the one that might be way over here at the very end, isn't touching the line. They're all a little ways from the line. And if you want to think about it this way, and this will be a harbinger back to means and standard deviation. Okay, think about this regression line as the average of all the data points that we have here. Okay, and we want to have the best average. And we know it's an average because all these data points here fall a little way from the line, right? Each one of these is a little bit of a distance away from the average. This is why at the beginning of the semester I said this chapter 2 part with means and variance and means and standard deviation in particular was so important because it keeps popping up again and again and again. And we see it here in simple linear regression. It's harder to see in multiple regression, but in simple linear regression, what do we have here again? We have averages and we've got individual distances from the average. The only thing that's different is that this line has been quantified for us so that the distances that we see from all these data points, all of them together, have been minimized. This is what we call the best fitting line. And there's no other way. If you're to move this line this way a little bit or this way a little bit, you would actually change the overall average distance all these data points are from the line. Now, I'm jumping way ahead of myself, and I'm going to show you a mathematical explanation coming up. So bear with me if I repeat myself. But this is how regression modeling works, and this is the extension from correlation. This slide here, I'm explaining slightly differently what I stated on the previous slide. We've seen that our simple model here, y equals beta x plus a, describes an imperfect linear relationship, right? So the value of y is not completely determined by x. Remember, it's also affected by random error. We saw that with analysis of variance. And so this is why you're never going to get all these data points fitting exactly on the line. You're going to have some aspect of random error that can fall into it, right? And so what we do with regression modeling, we try to fit this line through the scatter point so that the sum of the errors are minimized. Now, I didn't say sum of squared errors yet because that's coming up. So the sum of the errors are minimized, and that's what SPSS does for it, right? Then we have the straight line. It's the best fitting line, and now we can use it for explanatory purposes and also for predictive purposes. And if we want to extend our understanding a little bit better, we're kind of getting out there a little bit. This straight line that we have here, that's our model. Okay, this is our model. Go back to that slide where I said data, right? Data, all these data points here, data is equal to the model, this red line, plus the errors in prediction. Okay, so data, all these data points, is equal to the model, our line, right? This is our mathematical model, y equals beta 1 x, right, plus your a, plus the error, right? These are the error in prediction. So the model's not perfect. So this red line now is the model. Now, we've built our model, but we still have to test that model. That is to say, we still have to test whether or not the model is significant. Okay, and so hypothesis asks the question, is there a relationship, or can the model be used to explain something? Or did what we see that occurred, did it happen by chance? Okay, we've never left that. We do it with everything. Even with drawing lines between dots, we have to go, okay, is the line, is our model, is it statistically significant? Okay, so again, we're still doing the same thing. This is all about inference. We're pulling a sample from a population, creating a model based upon this sample, and we expect the model to operate in the population. And so what we're really looking at here is the slope of the model itself, because that kind of is the main function, right? That actually changes the x. That actually is a product with the x variable, whatever the slope is, and that's going to influence the y variable. The intercept a notwithstanding, that's going to be one of our starting points. And so we test the population slope. We test to see whether or not the slope is 0. So the null hypothesis in a simple linear regression model is that the slope is 0. And we want to know, is the slope that we have, that beta 1 in our y equals beta 1 x plus a, is that beta 1, is it different from 0, or enough different from 0 that we can say that there is a significant difference? And we have to know if there is a significant difference here. Again, this kind of goes back to inference, right? If the slope is significantly different than 0 in our sample, then we can expect it to be significantly different in the population. Understand also, this is where we start getting into prediction, right? I can create a model based upon a sample from a population. assuming that my sampling technique has been strong and I've used random sampling. Don't always have to. You can still use convenient sampling and other methods. Nevertheless, now I'm going to take my model and predict it by using another sample from the same population. Okay, and this is where we start getting into the validation of models. Yes, I've created a model that is statistically significant. Does it really work in the real world, right? And this is one of the larger steps that we see that sometimes is missing in the literature. The development of a model, we say it's statistically significant, but then we actually have to go out and test the model. And sometimes it's hard to test the models. Other times it's not hard to test the model. It's a little bit easier in the physiological sciences to go and test these models. And if the model holds true, that is to say you can actually predict something in the future based upon a model, then that gives your model a certain amount of validity. Okay, and it's called the validation of models. It's one of the things that we don't do enough of in the literature. Or right, so we should expect the same. We should expect the same thing happening. That validates the models. The hard part comes when someone goes and publishes a paper with a model, and then other people go along and try and replicate the study, and they can't replicate the findings. Okay, which means that they can't validate the model. That becomes a problem. And so this is why we do things. We develop a model, and then we try it out in the population. It could be a different sample in the population. And we should see whether or not the model can be validated by its predictive properties. But before we get there, let's go back to what we were talking about in terms of whether or not our model is significant. And again, we're still with simple linear regression. All we're looking at right now is if that beta 1, is it statistically significant or not? And so we have here on this slide, this is what the null hypothesis is with data points. I've got a scatter plot of data points, and if I were to run a straight line through the data points, I would get an R value of 0, which means there's no relationship. X has nothing on Y, doesn't cause an effect on Y, nothing like this. However, if my data points on the right-hand side here, right? So this is my null hypothesis. What if I've got something like this? I've got an R value, in this case here is 0.71, again kind of going back to correlation. Is the slope of this line here, is it different enough from the null hypothesis for us to say that this model actually has some validity to it, at least statistically? Is this model here statistically significant? Is the slope of the graph different enough from this slope so that we can say that there is a significant difference? And you might have been picking up on it a little bit here. If not, that's okay. And I said before, correlation plays a role in simple regression, and I talked about the R value in the preceding slide. And what I want to tell you is this: you may have figured it out already. This beta here, if this is the slope of the graph, this is the Pearson correlation coefficient. Okay, and this is why there's that strong connection between correlation and regression. Regression, we expand something. Regression, we expand it to we have a y-intercept, and we can actually use it to predict something. You can't do that with correlation. Correlation simply just explains the relationship. We tack on a couple of things here to give us a stronger explanatory power, especially with multiple regression. And in the case of linear regression, we can do some sort of prediction. Okay, so and I want to highlight this sentence up here. When there is a single independent variable, simple linear regression only, okay, the standardized beta coefficient thing here, this here, is equal to the Pearson correlation coefficient. So this is how correlation fits into our model. Okay, but we still haven't explained how SPSS actually picks whether or not the model is significant. I want to get into that with you. We're going to get back to those error aspects now. So still with hypothesis testing here, we're going to review something we talked about earlier in this presentation, and we're going to add in something new for us to consider. And the first thing is the error of the estimate. So when we saw before on the previous slide, you saw that when we had a visual of our scatter points, right, we had X and Y, we drew a line, a best fitting line through all those data points, and we saw that each one of those data points did not fall from the line. Some were very close to the line, but some were further apart. And so each one of those data points had a particular aspect of error associated with it. Remember what error means? It's a movement away from something. And that movement away was from the average line, so to speak. And so the error of estimate is how much each data point differs from the predicted, where we thought that data point should be, right? And where that data point should be is on that line. And so that gives us some information. But just like with means and standard deviation, you've got something similar here with regression. And so we don't have a standard deviation with regression lines, right? What we have is the standard error of the estimate. And it's a measure of how much each data point on average differs from the predicted data point or the line. Okay, so we take up all those error of estimates, right? All those differences there, and we take an average of all of those. Okay, that's what this is. So that's the standard error of the estimate, or the SEE. And this is why before, when we were talking about the standard error before, when we were linking that in with confidence intervals, I was very careful to call it the standard error of the mean, because now we have a standard error of the estimate. Okay, and we're going to expand on that in the next couple of slides, and I'll show you an example graphically of how this works together. And so the method that SPSS uses to fit a line to the data points is called the ordinary least squares method. Okay, what SPSS is doing when it's putting together a regression model for you is it finds a line that if you were to sum up all the differences or all the error scores together, sum them all up, it would have the least amount of total error. That's what the OLS is doing. Now, it's called the least squares because you might have guessed already, we always seem to have to square these differences. And so that's what's coming up in the next couple of slides. I'm going to show you exactly mathematically what is going on when SPSS uses the ordinary least squares method to compare a model to the null hypothesis. But the least squares method here again, just to kind of conclude with this, it's a method that finds a line that minimizes the sum of the squared differences, or the sum of the squared errors between the individual data points and the regression line. This regression line here is what we call the best fit. A movement up or a movement down would actually increase the total amount of error. And so the ordinary least squares minimizes the amount of error to the very end. This is an example using 4 data points, so we'll keep it fairly simple in terms of showing how SPSS works with the ordinary least squares mechanism to compare both the null hypothesis and a model that has been developed, and it does both, right? Okay, so we have here our four data points here, and what we have here in the model again is on the x-axis we have these values here, and on the y-axis we have these values here. And we don't know if we see a pattern or not because you only have 4 data points, which is very, very small. But what regression does is, we're going to compare 2 lines here, is it puts together a model for us. Okay, so it's going to fit the ordinary least squares for our model here. And notice what it does with our model that has been created. It lets us know that there's going to be a distance between this data point here. So data point here 1, 2. We thought that with our model x should perfectly predict y. So we predicted that y would be 1. But y wasn't. Y was actually 2. And so there's a difference of a value of 1 from 2, right? That's what the y was, to where y should be, which is 1. And so what the least squares method, does is it takes the difference between what the value was from what the value should be, and it squares that difference. Okay. Then it's going to add it to the next data variable on here, which is 2, 4. The model that we had predicted that if x goes up by 2, then y should also be 2. But it's not. Y actually turned out to be 4. And so in this case here, you've got a 4, or y, minus 2, where it should be the x, and we're going to square that. And we do that with the other 2 ones as well. Okay, so for each one, we do this. At the end, when we sum up all these squared differences, we get a value of 6.89. So this is the SEE here, right? It's the what is it? It's the standard error of the estimate, 6.89. Okay, so that's of our model. Now we also have to compare it to the null hypothesis, right? So the second line is horizontal because it's the null hypothesis, and this means the R value is going to be an R value of 0. Remember, with our original data points, you can still have an R value, okay? Now what we want to know is how far, we want to also know the same thing, how far each of these data points are from the horizontal line or the null hypothesis line. And so the same thing is done. We add up all those differences and we get a value here of 3.99. Now what we notice here, the value of 3.99, the SEE, or the standard error of the estimate, is less than the model SEE, or standard error of the estimate. And so we know that less error is better, or a better fitting model, or a better explanatory model than what we have here. And so we have to say that, at least in this case, the null hypothesis, that is to say, these data points here, how it all worked out, a better explanation for what we see here in terms of the real world is that this happened by chance. And our model is not significant. We can't use our model to explain y based upon a value of x. We can't use our model to explain anything in the future in terms of its predictive power, because chance is a better predictor. So that's in this case here, and I've written this out for you here. The smaller the sum of the squared differences, the better the fit of the line to the data itself. In this particular case, because the null hypothesis had the least sum squared errors or differences, it is a better explanation of the data that we see. Now, what happens when we have a significant difference is that this value of the model will be much less than the value of the null hypothesis. So when the SEE of the model is much less than the SEE of your null hypothesis model, then we say that there is a significant difference and the model is statistically significant, and then we can go ahead and use it to explain things and to predict things. The last two slides here, I'm going to, again, we come back to outliers. Remember those pesky outliers? Just when we thought they weren't going to cause any more trouble, they show up again. And so again, and this is what we look for in some of the preamble before we actually run a regression model. We take a look at all kinds of things in behind the scenes before we go, yeah, we're good to go to create a regression model. And one of them is you actually look for outliers in your data. And so notice what can happen here if I've got an outlier. Take a look, if you would, at where we see the slope of the graph now. Okay, the slope of the graph is running this way again because we've got all these data points here, including this one up here, right? You got that little data point there. What do you think would happen if you'd actually taken out this data point? If that data point here hadn't been there, what do you think would happen to that line? That line would probably be dragged much more closely here, and the slope of the line would actually be different than what it is. And so sometimes outliers can actually change the slope of the graph and might actually influence some level of significance or non-significance, depending. And so outliers can have an effect, which is why we always have to go and take a look at outliers before we run a regression model. And so we see here again that this one data point here has an awful lot of power in leveraging or pulling on this regression line towards itself. If you'd taken this one away, this regression line would fall somewhere down here, but it doesn't. Because of the data point here, because it's an outlier, it drags the regression line further towards itself. Here's one more example of the influence of outliers. And we see here, we've got an outlier that's sitting again way up in the corner here, okay? So this data here is a bit odd. You've got a lot of cluster of values that are lower in their numbers, and you've got one way up here that is kind of outside the range. Now it looks like it's falling into a particular pattern, right? But this is still considered to be an outlier to a certain extent. Right, and one of the reasons why it's considered an outlier is we have no data in here. Okay, for some reason we've got no middle data, which would be really, really helpful for us in terms of understanding our model. And so this is where if you've got an outlier here that's on the high end of the values, on the x value it's 10 and the y value is 5, it's the only one that's way out there, and all your other ones are between 2.5 and 2.5 down here, you're missing some data. And so you might have to go back and actually sort that out, or consider this one to be an outlier. Let me ask you this question. What do you think this regression line would look like if you were to take away this outlier? Okay, think about it for a second. You take away that outlier. Now all you're dealing with here is the data points down here. What do you think that line would look like? Well, if you thought about something like this, you're correct. Right? This is going to be the average, pretty close to these data points down here if you took away this outlier here. And so this becomes problematic, and this is why we have to take a look at outliers. Either you got to go back and collect more data, or go back and take a look at why this outlier is if it's an outlier at all. If it is, then you're kind of stuck. What do you do? How do you sort out these problems, right? And this is why, for those of you going off to graduate school, and even those of you who might be doing an honors thesis, undergraduate honors thesis, this is why you have committees. You always work together as a team to do the problem solving, to actually account for these issues. Let's look at an example here then, and this is comparing or looking at the relationship or the predictability of aerobic capacity and running performance. So here we have how fast, in terms of time, a person can run a 10-kilometer race is dependent in part upon their aerobic capacity, which we call VO2 max. And so VO2 stands for the volume of oxygen consumed, and that's the maximal amount of oxygen that is consumed. So the question is, can we predict 10-kilometer running times using VO2 max values? Or can we at least put together a model that might explain that? So we're going to put together a model, and then I'm going to give you a piece of canned data that shows some aspect of prediction based upon this. Also understand that in the research literature, you are rarely going to see a simple linear regression model. You will see multiple regression models. You will rarely see linear regression models, because you know as well as I do that the world is complex and many independent factors can influence the outcome of one factor. And so it's better to look at multiple variables and their interactions and influences on one outcome or y or dependent variable than it is to simply looking at things in isolation. But we need to do one for the linear regression, and then we'll move on to the more complicated multiple regression. So this is part of what we would do with this type of study. We would bring someone into the lab, and we would actually measure their maximal oxygen uptake. And then what we would do is we would take them and then have them go and run a 10-kilometer running race. And then what we would do, we'd have two pieces of information. We would have the X variable, which is their VO2 max from the lab. And then we would have the Y variable, which is their running time for a 10-kilometer race. And then with those two values, we would put together, using SPSS, a simple linear regression model. Here is some data that we assume to have collected. Again, this is canned data, and the yellow values are the VO2, the oxygen carrying capacity values, and so we have this in milliliters per kilogram per minute. You don't have to worry about that. And then the 10-kilometer times in the white columns, and again, this is the number of minutes it took to run 10 kilometers. And so with linear regression, we can afford to put together a scatter plot, right? Because it's only one variable against another that we're looking at. And so we can see visually an overall average pattern. We can detect the direction of the pattern. Sometimes, again, just like with correlation, the regressions can be either indirect or direct. That is to say, you can either have a positive slope or you can have a negative slope to your regression line or to your model. Right? And then we can take a look, just using eyeballish, we can kind of take a look to see if the data points fall away from the overall average pattern, which again is our regression line or regression model. It also allows us to take a look for any potential outliers. We have some simple conclusions when we graph our data here. We can see with the scatter plot Again, this is VO2 versus running time. We see a pretty clear pattern here. Notice that the pattern, however, is indirect or negative. That is to say, if you were to draw a line through these data points here, as we'll do on the next slide, you'll see that it is an indirect relationship. That is to say, as the values of x go up, y actually goes down, and so the slope would be negative. But what we see here is time is pretty much linearly related to VO2. As time decreases, running times decrease as VO2 increases. That's the nature of the relationship. And the data points are fairly close to the line. I don't really see any outliers here in this particular data set. But let's take a look at the next slide. When we draw our line, our regression line through the model, or I don't do it, actually SPSS does it, this is what we see. And this is actually, I've actually drawn this through Microsoft Excel, not SPSS, and that's fine. We still notice a couple of different things. Number one, most of the data points run fairly close to the model. And if you take a look at our model here, remember this again is data equals model plus the error. Now, this is where it gets can be a little bit confusing. The actual model, we don't know what the y-intercept is here. We have to draw this line up here. And before I said, when we're talking about simple regression, it's y equals beta x plus a being the intercept. This is true when you're talking about trying to find out your absolute values. But in this case, it's not. This really is our model. And we said before that the model is the data is equal to the model here, which is this value here, negative 0.7402x, plus the error. And the error simply allows us to fix the model to predict y. That's what it's doing here. And so this is what we would use to predict someone's running time based upon their oxygen carrying capacity, right? Because x is going to be the independent value, which is the oxygen carrying capacity. Notice also that the slope of the line here is negative. This is an indirect relationship. That is to say that as oxygen carrying capacity increases, what happens? Time actually goes down. And so this is why we have a negative value. If the data points were on this graph were in the opposite direction, you would have a positive value. Let's just take the model here and take a look at it on the next slide where we actually run a prediction using numerical values. And so now that we have our model, we can actually do some level of prediction. So let's say that I brought someone into our lab, now that we have this model here, and I were to run them on a treadmill, and I got their VO2 max. And let's say their VO2 max was 42 mils per kg per minute. How long would it take, or how long should it take them to run a 10-kilometer race based upon this one value alone? And so we would simply just plug in 42 into the x value here, and then we can actually solve for the equation. And we'll do that on the next slide. So now we're using our model to actually predict. If our model holds any kind of water, this is what we would see. When we put 42 into the x value, and I solve for the equation now, because again we've filled this value here. This is what we see. We work it out. This is going to be minus 31.09 because we're multiplying a negative value by a positive. So we're going to get a negative value. Negative 0.7402 multiplied by 42 gives me negative 31.09 plus the correction factor here. And in this case here, we come out to 61.8 minutes. So this would be our prediction. Now, if our participant went and ran a 10K and it came out to 63 minutes, that's actually pretty good for a level of prediction. Again, there's the terrain, and there could be wind conditions and the time of day of the running, all those different factors that can add in a little bit of error to what we think should happen ideally. Now, if it came out and this person ran a 10K time in 75 minutes, well, that's either chalk it up to a bad day, the person might have had the stomach flu, maybe we need to go back to the drawing board, or VO2 is just simply not powerful enough. And so this is what I mean by validating models. You actually have to take them and actually run them in the real world to see if they actually work. we've finished this topic here with respect to introduction to linear regression. And so this slide and the next, just a brief summary. So regression models allow for the explanation and prediction, in some cases, of outcome variables. Just a kind of an aside, even though we kind of touched only on simple linear regression here, that first statement is kind of important. You're going to see an awful lot of regression modeling in the research that you read. If you're reading primary journal articles, you'll see regression. There's different forms of it. Yeah, you will see a lot of it, and it's incredibly handy in terms of a statistical tool. Again, remember that models always incorporate some form of error, and so models never perfectly mimic what's happening in the real world. That is to say, as we see in the second bullet point here, the data, the real world, what's happening there is a combination of both the model, our best estimate of what's going on, plus error, which always occurs for a variety of reasons. And the simple linear regression really is just a sidestep over from Pearson correlation. There are a couple of minor differences, and I've posted a video for you to watch to show you when to choose either correlation or simple regression. Not all models are great. Some models fit the data better than others, and so what we try to do, again, in the real world of research is develop a model that is what we call best fitting. And we'll get more into the aspect of total variance when we get into multiple regression in the next topic. But the mechanism that we use, or that SPSS uses, is called ordinary least squares. And so it determines which model minimizes the amount of error that falls in between the data points when you're trying to create your model. Okay, and this OLS, or ordinary least squares, is then compared to the null hypothesis. And the model, either the OLS variance model that SPSS puts together for you, or the null hypothesis model that SPSS compares to, whichever one of those models has the least amount of error, that will be the best fitting model. And this is how we choose whether or not to say our model is statistically significant or not. If the null hypothesis model has less error than your model that you've created, based upon your research, then we say, yeah, the null hypothesis is better, and so it's a higher chance that your findings happen by chance. If your OLS data has minimized a lot of error, and the error in your model is much less than the null hypothesis, then we go back and we say, yeah, it's whatever's happening here with this model likely didn't happen by chance, and so we're going to go with the model that you've created because it's a better fitting model and it explains more.